This is Mr. Hassan's Maths channel. I'm now answering question number 10 from the May-June 2023 Pure Mathematics Paper 3 from Cambridge 9709. This is Paper 3 Variant 1. And this question, part A, is to do with the factor theorem, basically. It says the polynomial x cubed plus 5x squared plus 31x plus 75 is denoted by p of x. So basically they're saying p of x is equal to x cubed plus 5x squared plus 31x plus 75. Now, they said that show that x plus 3 is a factor of p of x. Now, the simplest way to do this is basically to find the value of x that makes this bracket equals 0. So when x plus 3 equals 0, that occurs when x equals negative 3. And substitute that value of x inside the function p and show that that gives you 0. If that gives you 0, that means that when x plus 3 is the divisor, if you divide this by x plus 3, you get no remainder, which means it's a factor of p of x. Okay, another way we could do it is we could do algebraic long division and show that the remainder is 0, but that's a lot more hassle than this. This is much easier to do in this way. Sometimes they would say use the factor theorem, in which case you would have to do what I'm saying now. So I'm going to say that if p of minus 3 is equal to 0, then x plus 3 is a factor of p of x. Okay, so if this is true, then this is going to be a factor. And so we have to, when we show this is true, we have then proved that is a factor. So this statement should be written down. It's very important when you're saying show that. So either at the end or before you start, you write this statement down and then show what p of minus 3 actually is in this expression. So you're going to have minus 3 all cubed, including the negative sign, plus 5 times minus 3 squared, plus 31 times minus 3 plus 75. Okay, so what will this give us? This will give us negative 27, because when you raise a negative number to a odd power, it stays negative. And this is going to be plus, and you're going to have 5 times positive 9, which is 45, because a negative number raised to an even power gives you a positive value. And you're going to have 31 times negative 3, which is negative. That's going to be 93. Okay, 31 times 3 is 93. And you got plus 75. So what this will give us, well, you have 45 plus 75, which is 110 plus 10, that's 120. And you got minus 27 minus 93, so you got 20, and 90 gives you 110. And 7 plus 3, so it's going to be negative 120, which of course gives us 0. So we can say, therefore, x plus 3 is a factor. Is a factor of p of x. And we've given the statement which, shows that over here. Statement that this condition is true, then it's going to be a factor. So that's something that we should state either at the end or at the beginning, right? But we've shown that as p minus 3 is equal to 0, x plus 3 is a factor of p of x. So there's the answer to part A. Now for part B. Okay, it says show that z equals minus 1 plus 2 root 6i is a root of p of z equals 0. So this was the function that they gave us. I just copied it down here so we don't have to keep scrolling up and down. So p of z is going to be equal to z cubed plus 5z squared plus 31z plus 75. This says basically replace the x in the function p with z. That's what it means. All right? And we want to show that this is a root of p of z equals 0. So very similarly, this is now given not as a factor, but as a root. So we can say if p of minus 1 plus 2 root 6i is equal to 0, then we can say minus 1 plus 2 root 6i is a root of p of z equals 0. Okay, is the root of p of z equals 0. If this substitute into there makes a 0, then it's going to be a root of it. Okay, so we have to now substitute this into the equation. This is one way of doing it. There's actually other ways of doing it as well. But this is one particular way of answering the question. Okay, we can substitute the values in and get the answer. Okay, so we could do it in another way as well if you wanted to. Okay, but this way I think is probably the simplest. All right, so basically now we need to have z cubed and z squared. So what I'm going to do is I'm going to do this separately instead of having like a long, messy kind of like expressions here. I'm just going to say, okay, let's find what z squared is. So we know z is minus 1 plus 2 root 6i. So let's find what z squared is first, and then find what z cubed is, and then we can deal with it. So we have minus 1 plus 2 times root 6i, and we want to square all of this. So when you square this, you're going to have minus 1 is going to be squared. That's going to give you 1. And remember the pattern for squared brackets. You then multiply these two terms together and then double the answer. So you're going to have negative. And if you multiply these together, you're going to get 2 root 6i. So now it's going to be double, so 4 root 6i. And then you square the last term. So you're going to have plus 2 squared is 4. Root 6 squared is going to be just 6. And I squared is going to be I squared. And remember, we know that I is equal to the negative square root of 1, which means I squared is equal to negative 1. So this becomes negative 1. So you're left with here 1 minus 4 root 6i. And you're going to have 4 times 6, which is 24, times minus 1, which is minus 24. So we're finally left with minus 23 minus 4 root 6i. So this is z squared. And now we want to find z cubed. Now we could use binomial expansion if we wanted to, but as we've already got z squared, I think it's easier just to expand these two multiplied with each other. It's probably a bit simpler to do that. And we got minus 23 minus 4 root 6i. So when we expand this, we have minus 1 times minus 23, which is positive 24. And minus 1 times minus 4 root 6i, which is plus 4 root 6i. Then we have root 2 root 6i times negative 23, that's negative 46 root 6i. And you have positive 2 root 6i times negative, so it's negative 8. And root 6 times root 6 is 6. And I times I is I squared. Okay, so this will give us 24. Okay, and this is going to be plus 48. Because this is going to be, sorry, this is going to, what am I saying 24? That's a silly mistake I've made there. That's supposed to be, sorry about this. It's minus 1 times minus 23, which is positive 23. Okay, I don't know why I wrote that. That's a bit silly of me, but I spotted it just in time before I messed up. It would have come up in the end anyway, because our sum would not be 0, but just avoid mistakes like that. Minus 1 times minus 23 is positive 23. Okay, so now this is going to be 23, and now this will be minus 48 times I squared, so it's going to be plus 48. And you're going to have plus 4 root 6i minus, so let's just do that sum, minus 46, so that's going to be minus 42. So negative, negative, it's going to be negative here. Let's just get the eraser out. That's negative 42 root 6i. So in the end, we can say z cubed is equal to 23 plus 48, that's 60, plus 11, that's 71, minus 42 root 6i. So that's z cubed. So now we can take this and put it into our equation. So what I'm going to do to make it a bit easier, I'll just bring this down here so we can see what we're doing. It's just instead of x, it's z, that's all, but oops. What did I do here? What did I do? Oh, this is there. No. I don't know what I did there. Is that supposed to be with this? I don't know. 1 second. Oh, it's supposed to be here. Sorry about that. I didn't want to take this with me. Okay, so we want to now replace z and z squared and z cubed into this expression. So we're going to have p of minus 1 plus 2 root 6i is going to be, so you're going to have z cubed, which is 71 minus 42 root 6i. That's z cubed. Plus 5 times z squared. Z squared is negative 23 minus 4 root 6i. I'm going to have plus 31 times z. And z was minus 1 plus 2 root 6i. And in the end, we have plus 75. So we should hopefully get 0 when we simplify all of this. So 71 plus 75 is 146. So we've dealt with those two. Now we've got to expand the bracket. So this is minus 42 root 6i. And that's going to be minus, that's 115, minus 115. I'm going to have 5 times minus 4, which is negative 20 times root 6i. And then we're going to multiply this out. That's negative 31. And it's going to be plus 62 times root 6i. Okay, so now we got 146 minus 146, which is good, because minus 115 minus 31. So if you do 115 and 31, add them together, you get 146, but they're both negative. So it's going to be negative 146. And minus 42 minus 20 is minus 62 root 6i. So we dealt with those, and we got plus 62 root 6i. So we can see here, everything cancels out. That gives you 0. So we can say minus 1 plus 2 root 6i is a root of pz. Okay, and we gave the reasoning for it over here. Okay, if this is true, then it's going to be a root, and we've proved that this is true. Okay, so there's the answer to part B of this question, and now we're going to go through part C. Okay, now for part C, it says, hence find the complex numbers z, which are roots of pz squared equals 0. So now we have an important word, hence. Important instruction, hence. Hence, find the complex numbers z, which are the roots of pz squared equals 0. So we got to find the roots of this equation. Okay, pz squared equals 0. So we need to use some of the information that we already found, which is listed here. So we prove that x plus 3 is a factor of px. We know that px is equal to, we know that p of x is equal to x cubed plus 5x squared plus 31x plus 75. All right, and we know that z equals minus 1 plus 2 root 6i is a root of pz equals 0. Now, so we want to use these facts to try to work out all of the roots of this equation, pz squared equals 0. So let's first of all find what pz squared is as an equation, p of z squared. So we're going to replace the x now with z squared. So instead of x, I'm going to write z squared. So I'm going to have z squared raised to the power of 3 plus 5 times z squared raised to the power of 2 plus 31 times z squared plus 75 equals 0. We've got to solve this equation over here. Let me just fix this. This is z squared squared. All right. So this is basically going to end up as z to the power of 6. You're going to end up, I'll just write it on the side, z to the power of 6 plus 5z to the power of 4 plus 31 z to the power of 2 plus 75 equals 0. So here we know we're going to have 6 roots. There's going to be 6 roots. They could be real roots. Some of them could be real roots. Some of them can be complex roots. Okay, but because it's raised to the power of 6, order 6, there's going to be 6 roots. So we got to find all of the 6, or all of the complex roots. Okay, so it could be all of them are complex roots. We'll have a look and see. All right. So we've got this equation here. Okay. And what we can do is we want to try to find the roots of this equation. Okay. So what we could do, we could write it like this if we want to. Let's have a look. Z squared equals 0. Okay. So I could write it like this: z squared. I was thinking about doing it a different way, but let's just do this: plus 5z to the power 4 plus 31z squared plus 75 equals 0. Okay. And what we can do here is we know that x plus 3 is a factor of p of x. So x plus 3. So I'm going to use this fact now. So this is the hence part. I'm going to try to use this fact. So x plus 3 is a factor of p of x. Okay. Which means, okay, so if x plus 3 is a factor of p of x, then we can say that, replace the x with what? Z squared. We can say z squared plus 3 is a factor of p z squared. Okay, so z squared plus 3 must be a factor of p z squared. I've just replaced the x with z squared. If this is true, then this is true. Okay, that's using this information that we found in the earlier question. That's where the hence comes in. So that means if z squared plus 3 is a factor of pz squared, okay, then we can say that z squared plus 3 equals 0 will give us roots. That means z squared is equal to negative 3, which means that z is equal to plus or minus the square root of negative 3. Okay, and we know we're looking for complex roots, so we can basically think of this as plus or minus root 3 times root of minus 1. And we know that I is equal to the square root of negative 1. So this is going to be I. So z is equal to plus or minus root 3 times I. So we can say that one of the roots is root 3i. Another complex root is negative root 3i. So we found 2 of them. We've got another 4 to find. How do we find the other 4? Well, we can use this. We can use this to find the other roots. Okay, so z equals minus 1 plus 2 root 6i is a root of pz equals 0. All right, so if this is true, we can now relate it to what we have. If z minus 1 plus 2 root 6i is a root of pz equals 0, then we can say that minus 1 plus 2 root 6i, then, sorry about that, oh, 1 second. Then we can say, let's get rid of this. If z equals minus 1 plus 2 root 6i is a root of pz equals 0, then we can say z equals minus 1 plus 2 root 6i is a root of pz squared equals 0. Okay, then z squared equals, so if z equals minus 1 plus 2 root 6i is a root of pz equals 0, then z squared is equal minus 1 plus 2 root 6i is a root of pz squared equals 0. I've just replaced the z's with z squared. Okay, so this is a root of this. So z squared equals minus 1 plus 2 root 6i. 1 second. Plus 2 root 6i, all right, is one root, okay, but that's z squared. We want to find what z is, okay, and we also know that as they come in conjugate pairs, that z squared equals minus 1 minus 2 root 6i, because if what we can say is basically there's 2 things that come out of this. Okay, let me just write that down there as well. Okay, if this is true, then we can also say then z equals minus 1 minus 2 root 6i is a root of root of pz equals 0, because the roots come in conjugate pairs. So if this is a root, then this is a root, and this will mean then z squared equals -1 minus 2 root 6I is also a root of pz squared equals 0. So now we can try to find what z is. Okay, if we find what the z's are for these, we have basically answered the question. It's basically, we need to find what the square root of this is and the square root of this is. If you find the square root of this and the square root of that, we will have our last answers. Okay, we'll have z3, z4, z5, z6. Okay, there's 6 roots. Okay, so now, how do I do this? Well, we can say let z be x plus I times y. It's a complex number. Okay, so then that means x plus I times y squared is equal to -1 plus 2 times root 6I. Okay, and so we want to find the values of x and y for which this is true, and that will therefore be our complex number z. Okay, so what I'm going to do here is I'm going to square this. I'll have x squared plus the middle term is going to be I squared times xy times, sorry, it's going to be 2 times x times iy. So 2xy times I, because you to square the bracket, you square the first term, you multiply these together, x, y, I, and then you double it, and then you square the last term, so you're going to have plus I squared times y squared, and that's identical to this -1 plus 2 root 6I. So this -1, remember what I squared is equal to -1. There's going to be x squared minus y squared will be the real part of this complex number. And plus 2xyi, well, this is the coefficient of the I, so this will be the imaginary part. And that's identical to -1 plus 2 root 6I. So what we can say here is that this is the real part. This is the real part, and this is equal to -1. And we can say that this is the imaginary part, and this is equal to this. Right? So if we compare the coefficients of the real parts, we have x squared minus y squared equals -1. And if we compare the coefficients of the imaginary parts, we have 2xy is equal to 2 root 6. So the 2's cancel out. xy equals root 6. So these can be solved simultaneously. Okay, these can be solved simultaneously. How much space do I have? I have space down here. So I'll carry on down here. So I can rearrange this and I can say let y equals root 6 over x. Therefore, we can say that x squared minus root 6 over x all squared is equal to -1. So x squared minus 6 over x squared is equal to -1. I can multiply both sides by x squared, have x to the power 4 minus 6 is equal to -x squared. So I've got x to the power 4 plus x squared minus 6 equals 0. Okay, and now what I've done is I'm trying to solve this equation, multiply both sides by x squared. So I can solve this. This is like a disguised quadratic, but I can just think of this as x squared times x squared is x to the power 4. The middle term has to be the basically two numbers in the brackets must multiply to give you -6, add to give you +1, so it's +3 and -2. So we can say that x squared equals -3. So x is equal to plus or minus the square root of -3. Now x must be a real number. X must be a real number, so we can't accept this. So x squared is equal to 2. So x is equal to plus or minus the square root of 2. So x is a real number, so that's fine. So we can say that when x is equal to root 2, then y is equal to root 6 over root 2, which is like root 3 times root 2 over root 2, which is root 3. So when x is root 2, y is root 3. And when x is minus root 2, y is equal to minus root 3. So that leads us to our z3 is equal to root 2 plus root 3 times I. And the fourth root is root 2 minus root 2 minus root 3 times I. So we have now 4 roots. So we have z3 and z1, z2, z3, and z4. Okay, so now once we've got these answers, we've got now Z1, Z2, Z3, Z4. Now to find Z5 and Z6, we could go through the whole palaver of doing all of this again for the other, roots, which was, we said Z squared equals -1 minus 2 times root 6i. But to save time, we know that the roots come in conjugate pairs. So if Z1 is root 3, then Z2 is going to be minus root 3. And if Z2 is equal to, Z3, sorry, is equal to root 2 plus root 3i. Okay, I've called this Z2 equals this, and we call it Z3 equals this, and we call this Z4 is equal to minus root 2 minus root 3i. These are the ones that we found. But we know that there must be another root which is a conjugate of this root. Means there must be the same numbers but with the opposite sign between them. Okay? Because complex roots always come in conjugate pairs. So Z6 must be minus root 2 plus root 3i. So these are our 6 roots. I could go through the whole of this process again using this. Okay, as same thing I did there, I could do it for this, and I'll end up with the other 2 roots. Okay, but because I know that they come in conjugate pairs, I don't have to go through all of that whole process again. I can use the fact that I've got these 2, I found these 2, and the conjugate of these 2 is also going to be roots. So root 2 plus root 3i, root 2 minus root 3i, minus root 2 minus root 3i, minus 2 root 2 plus root 3i. So here are the 6 complex roots. Okay, all the roots in this particular case are complex. Sometimes you have some roots which are complex, some which are real. Okay, but the complex roots always come in pairs, conjugate pairs. Okay, as we said. So no need to go through the whole palaver again. We can just take the roots that we know and say, okay, the other one must be the conjugate of this, and the other one must be the conjugate of that. Right, so we have now solved this problem. Question number 10 from the June 2023 paper 3 variant 1 pure mathematics 3 from the Cambridge 9709 syllabus. Other questions from this paper will be found in the playlist that will appear on the top right of the screen at the end of this video. Other questions from the topic of complex numbers you'll find in the playlist on the bottom right here. You can subscribe to my channel by clicking on this link, and the video on the top here will show you how to use my channel to find the material that you're looking for. Thank you for watching, and see you soon.